One of the goals of today's lecture is going to be to explain why we care about vector quantities. Last time, we learned that assigning a direction to a vector quantity is crucial, as this resolves any ambiguity. We will learn in this very last topic in topic 1 that the direction also has implications when combining vectors in calculation. Understanding this idea that some quantities have direction is the key to correctly manipulating quantities. To understand how vectors combine, let us take a look at this example. Consider a plane leaving a city and flying 550 kilometers north before changing direction and flying 250 kilometers west to another city. What is the sum of these two vectors? In other words, if the plane wants to do it all in one shot along a straight line, what is the distance it will travel? It's obviously not 550 kilometers plus 250 kilometers. Let us now consider another example. Suppose we have these two vectors a and b. In general, they have different magnitude and pointing in different direction. The question is, what is a plus b? What is the resulting vector when these two vectors are combined? Here's the rule to add two vectors. First, the tail of the second vector is placed at the head of the first vector. So what we do here, we move vector b around such that the tail of vector b is at the head of vector a. From last lecture, we learned that we can move any vector as long as we keep the magnitude and the direction the same. It still describes the same vector, no matter where the vector is located now in space. The second step, the sum or the resultant, is obtained by drawing an arrow from the free tail to the free head. This vector in red is the result of adding vector A and vector B. It should be noted that the length is not equal to the sum of the lengths of vectors A and B. The direction is determined by rule number 2. The rule can also be extended to more than two vectors. When adding more than two vectors, there are a number of constructions we can use to find the sum. Suppose we have these three vectors a, b, and c. What is a plus b plus c? First, we could add vector a and vector b to get this red vector. We then add this vector in red and vector c by the same process to obtain the resultant vector a plus b plus c, indicated by this black arrow. Or we could add vector b and vector c first to get this red vector. We then add vector a and this red vector to obtain the resultant vector a plus b plus c. This shows how a vector sum doesn't care about the order of its terms. Or we could add vectors a, b, c directly in succession to get the resultant vector a plus b plus c. Or we could add vectors a, b, and c in any order and still get the same vector. To summarize, this is what we do in vector addition. Given any vector a and vector b, we can find the resultant vector c equals a plus b. This process can be reversed. We can think of it this way. Given any vector c, this vector can always be expressed as the combination or the sum of two vectors a and b, such as this, or this, or this, or any other infinite combinations of a and b. However, if vectors a and b are chosen to be perpendicular to each other, they can be both treated separately, since they are linearly independent of each other. The term linearly independent comes from vector analysis, which means that if two vectors are linearly independent of each other, it is not possible to write one as a multiple of the other. Vectors a and b here are referred to as components of vector c. A is the horizontal component and b is the vertical component. Given vectors a and b, the length and the direction, we can find this vector c using the rule in vector addition. The length of vector c is calculated using Pythagoras' theorem, c squared equals a squared plus b squared. Given the vector c and the angle, we can find the length of its component using simple trigonometry. C here is called the hypotenuse, the longest side in a right-angled triangle. A is known as the adjacent side because it is adjacent to the angle. And B is called the opposite side since this side is opposite to the angle. Sin theta is equal to opposite over hypotenuse, or B over C in this example. And from here, B, which is the vertical component of C, is equal to C times sin theta. Cos theta is adjacent over hypotenuse, or A over C. And from this, the horizontal component A is obtained by multiplying C and cos theta.